Okay, we're moving into week 2. Hopefully, people are finally getting their books and getting access to the whole course, so you can really tag along this week and get caught up with everything. This week, we're going to talk about the atmosphere, a little bit about the origin of science thinks may have happened, but really the composition and structure of it, which we're going to deal with. So that's what I'm going to focus on right here. So, what is the composition and structure? Well, all around the world, the atmosphere is interconnected. And one of the things, a case in point here, they were showing you the Saharan air layer. I don't know if you noticed it over the summer. There was a big bunch of news about a large Saharan air layer moving across the Atlantic Ocean and into the southeastern U.S., the Caribbean. It even reduced Puerto Rico, some of the visibilities, to a quarter mile in dust. Basically, what it is dust. It comes in from Africa. Huge thunderstorms sometimes form over the desert in Africa, and they blow out dust, sand, and it moves across the Atlantic. When it does, it interacts with hurricanes and all and reduces them. And we'll talk about why that is later. But they can come into the United States, obviously Puerto Rico, and they can come into Southeast United States. Sometimes they create really pretty sunsets, you'll see. So weather is you all have discussed memorable weather events this past week. And one of the reasons I did that was to just get you thinking about all the different kinds of weather that you've dealt with and you've seen and how they impact your daily lives. So, what is the atmosphere? We'll start with that. There's an Earth system which consists of the atmosphere, the hydrosphere, the geosphere, the biosphere. Each one is interrelated. What happens in one impacts another. So, what happens in the atmosphere does affect the hydrosphere. It can affect the geosphere or even the biosphere. So, they're all interrelated. So, that's where we start from. You think about the Earth's atmosphere is relatively thin. It's a tiny layer, really, around the whole mass that we know as Earth. Roughly 99% of the mass of the atmosphere is within 32 kilometers or 20 miles. Think about it. You drive down the road 20 miles. Not real far, is it? That's about how thick the atmosphere is. Not real thick. But sure has an impact on your daily lives. So we talk about the lower layer of the atmosphere. And that is where things are pretty well mixed. That's why it's called the homosphere. And in this layer, nitrogen is the main gas. 78% of the atmosphere is made up of nitrogen. Another 20 or 21% is oxygen. Both things we kind of need. However, argon is almost 1%, and carbon dioxide is way down there at 0.05%, roughly, or 0.04. However, that has been increasing here over the last 30 or 50 years. So here you can see the distribution of that. Now there's also aerosols that get into the atmosphere. Oh yeah, and water vapor. Water vapor is consistently less than 4% at any one location. It's usually in the lowest 1 kilometer of the atmosphere. But it sure is going to play a role in what we talk about in weather. Carbon dioxide, required for life, photosynthesis. But both carbon dioxide and water vapor absorb and emit infrared radiation. Guess what? Next chapter, we're going to be talking about that in depth. Here you have air pollution. A lot of air pollution is man-made, but there is a lot natural. Plants decaying, pollen, volcanoes erupting, dust storms. There was one last week out in Phoenix, Arizona, that actually closed the interstate that goes through Phoenix from a dust storm. Oh yeah, all those fires out in California right now, they're putting up a lot of pollution in the air. So another part of this is we're going to talk about the scientific method. You can see the different parts of it here, but I'm going to describe an event that I kind of took a part in and was involved in studying. It's not necessarily something you deal with in Ohio, but it's something I deal with living east of the Appalachians. The question was, why do some squall lines that come across the Appalachians die while others intensify and become more intense? It's a real difficult problem, especially if you live in Raleigh, North Carolina, or near Western Virginia, or even in Southeastern Virginia. So why does that happen? So the question was posed that, well, maybe it had to do with stability. And that is just a parameter that's in the atmosphere, something that affects like air balloons or how balloons rise. So we made an hypothesis of what we were looking for. We went back and studied it and compared that hypothesis to what actually happened in the atmosphere. We found some things that worked and some things that didn't work. So we changed that hypothesis again, reformulated, and actually came up with a parameter that actually does a pretty good job of predicting when squall lines that move across the Appalachians will intensify and when will they weaken. So with that was a scientific method applied to something in real time that was very important if you happen to live there. There are various atmospheric models. We look at things in physical context, such as Purdue's lab for simulating tornado vortexes. We look at numerical models. We also come up with conceptual models where we basically just put into words what we think about might represent a concept in the atmosphere or a part of the atmosphere. Numerical models are extremely complex and they're inherently wrong, just from the fact that we cannot solve the equations in the atmosphere with any accuracy. So the final part of this chapter is observing. In order to understand weather and forecast it in the future, you got to know what's going on now. ASOS is all over the place. It's basically an automated surface observing system. So it is almost any airport that you fly into and out of will have at least one, if not two, ASOSs. The idea is to get as much observational data in real time, and ASOS reports it every minute so that you can actually see changes in weather, changes in wind, changes in temperature. All of this pressure is important when you're trying to forecast and observe the weather. First things first, get it all down, what is happening right now. Remember, weather is now. And every 5 to 10 minutes before every hour, all over the world, ASOS or other automated systems, or even people are observing the weather, putting it out. It's all collected, and that is forming the weather maps that you're going to spend a lot of time looking at throughout this course. There are cooperative observing networks, basically volunteers. The Weather Service provides the equipment like you see here in the picture, and they record daily readings. The idea is to get a climate record for long term, finally getting some ideas of actually what is happening in the climate. And it's going to take years for this really to come about. But there is a lot of it going around now. COCORA's just a volunteer network. If you want to join, hey, that would be wonderful. But basically, it's just some group. It's people that are interested in taking rain, hail, and snow readings daily and passing them on to a national collaboration of networks so we can get a more detailed and accurate estimate of how much rain fell, how much hail occurred, where did the snow fall. Radiosondes are launched every day at 0Z and 12Z. Remember, we deal with Greenwich Standard Time. They go up to about 100,000 feet in burst. Basically, they burst because the atmosphere gets thinner as you go up. So the balloon expands and expands, and finally, it's gone. There's a parachute on it, so hopefully the package won't injure anybody. You could actually get one of these in your backyard. These are sent up at a location outside of Cincinnati. Wilmington, Ohio is one example of a location that sends these up. So say that one balloon went up, didn't go too far, it might drop at Mount Vernon. You never know. They provide a sounding profile of the atmosphere in the vertical. There's an instrument that's contacted with this. Dropsondes are put out from aircraft to collect data as they fall. They get wind speed, they get pressure. They're often deployed in a hurricane by hurricane hunter aircraft, especially in the eye, to get the pressure at the eye, to get the winds outside the eye and the eye wall. All of this information is out there. Remote sensing, radar, satellites. And guess what? The more information you can get, the better you can define this temperature profile that is what our atmosphere looks like. You'll notice temperature cools in the troposphere. So if you're going up in a mountain, the higher up you get, the temperature is getting colder. We'll find a reason for that in a few chapters later. Stratosphere temperature actually warms. The ionosphere is another layer where you actually get auroras that develop. They're caused by the solar wind. Solar wind can come out with more particles and can cause really spectacular auroras that may actually get down to our latitudes where we can actually see them sometimes. And you can see here numerical models trying to forecast the probability of an aurora. So all this is what you see in the weather. So let's just look at a couple things here. This week, you're going to be looking at weather maps. So I thought I would pull up a detailed one of Ohio. If you look at this weather map here, and I'm actually not sure of that location, what that is, what that station might be in Ohio, to be honest. Toledo, I believe, is right in there, but I'm not 100% sure. You probably know better than I do here. But the temperature at this station is the upper left-hand corner is 81 degrees. Dew point, which basically is a measure of moisture, is 63. The atmospheric pressure right here is 3 digits. If it's less than 500, you're probably going to be putting a 10 in front of it. If it's more than 500, you'd probably be putting a 9 in front of it. So a 10 here would be, this was 1014.6 millibars. That's a pressure at that surface, and it's set to be sea level. So it's adjusted so that even though this surface where this station is well above sea level, it's adjusted for sea level. And you can see on here, surface map. Here we have a plotted map with a stationary front. Oh yeah, one other thing. Here is the wind. Notice the barb pointing into the center here. You see this little barbed end? That's 5 knots of wind. A long barb is 10 knots. And a pendant is 50 knots. And the wind is coming from the south. It's a southerly wind today at this location. That's the direction it is pointing. Notice here, the wind arrow points this way towards this circle. That's a northeast wind. In weather, we always tell where the wind is coming from. So, finally, you're going to also look at STUV diagrams. What are STUV diagrams? Temperature plotted in the x-axis, pressure plotted in the y-axis. You just go across, plot the points. So right here, this is Detroit. Temperatures are plotted from radio sound, just like we were looking at earlier. And you get the wind here. And you're basically drawing lines that are connecting. And right here is a tropopause. So this is where the stratosphere begins, right in this area. Now, I'm going to show you a slightly different upper air sounding of this exactly same data. Exactly the same time. This was at Detroit. The reason I want to show you is this. We're not going to talk about it a lot necessarily, but in this course, I wanted you to be familiar with what most meteorologists use. Meteorologists use something called a skew T. So what that is T is skewed to the right. So temperature, instead of going straight up, goes like this to the right. Pressure, instead of being equal, is actually put closer together at the bottom and further apart at the top, just like the atmosphere does. And with that, what we can do if you're a meteorologist is there's a whole lot of potential with this to understand something called convective available potential energy, which is used in generation of thunderstorms. It's very easy to pick it out on these kind of charts. So that's one of the main reasons that meteorologists use this type of chart. But you're going to be mostly working with Stuvie diagrams. But I wanted you to get familiar. Notice here we have a little bit more emphasis on the warming that's occurring above about 125 millibars. So with that, that's where your stratosphere has begun. Your winds are shifted to the west there. You can actually see the wind change too as you go up through it. So hope you have a good week this week. Let me know if you have any questions.